Zealand innovation in forage brassica is that of cultivars able to be grazed multiple times. That concept provides enormous flexibility on farm. The development of herbicide-tolerant cultivars to enable simple, effective weed control has also been a very valuable breakthrough. More recently, the development of Rafno brassica has provided a resilient, multiple-grazed option for hotter, drier conditions. This is a truly revolutionary crop for which we can thank Andrew Dumbleton. The improvements in fodder, beets, maize, forage cereals and others have been very significant with a wide range of material available today. Overall, the broader range of pasture cultivars and fodder crops enables very smart farming systems that weren't possible in the 1970s. There has been much debate about progress in plant breeding for yield and persistence in pastures, but over time it is apparent from trials that there has been a steady improvement in both yield and persistence, as well as a wider range of cultivar types for different growth habits, flowering times, seasonal growth patterns. In reality, we must understand that genetics enables, it actually sets the limits, the management delivers how much is produced on farm. Not only has breeding contributed to New Zealand farming, it has had a significant impact globally. Although not usually discussed at New Zealand grassland conferences, the use and value of turf in our urban grasslands is substantial. Potentially, that's 2 to 4% of the area of pasture in New Zealand, depending on what's included. When I started, many sports fields were planted with ryegrass mixed with white clover, and were often substandard for players and spectators. Home lawns were from ecotypes harvested of brown top, chewings, fescue and crested dog's tail. Today, the top quality cultivars enable stunning sports fields to be presented. I have been involved in breeding turf cultivars, particularly ryegrass, incorporating endophytes and winter activity for winter wear recovery. New Zealand also today has been very successful in brown top breeding, and today we have a substantial seed exports. Germplasm is an essential source of new material for any breeder, and it's absolutely essential for a country like New Zealand, which has no native pasture species suitable for farming. For me, germplasm discovery has been one of the most valuable and interesting aspects of my career, and I'm very enthusiastic about it. Almost all the species we use in pastures originate from the European region, the key exceptions being prairie grass and paspalum from South America, kikuyu from Highland Africa. Each species, though, has a very different evolutionary history, and understanding these is crucial to understanding the genetic resources available. This diversity of germplasm and endophytes we use today is thanks to our Margot Ford Gene Bank and other international collections. For many breeders, the Margot Ford Gene Bank is a national gold mine. I discovered recently, though, after ordering samples from the Swiss Gene Bank, that not all breeders are like me. I was told I was the first person outside Switzerland who had actually ordered samples. One of the many interesting evolutionary studies I was involved in was that on cocksfoot. The European species have an amazing history of glaciation and reinvasion of northern Europe from Glacier refugia. I have been fortunate in being able to collaborate with researchers using molecular tools to understand the history of cocksfoot. After taking over 10 years or more to obtain samples from gene banks, the diploid cocksfoots, we were able to use chloroplast and ITS molecular sequences to show migration events. Commercial cocksfoot is a tetraploid evolving natural from adjacent diploid populations. Knowing this, we can actually develop a range of novel tetraploid combinations. What happens when we develop hybrids from distant populations that couldn't hybridize naturally? What happens when we cross the Spanish material with Chinese material, a Moroccan material with Himalayan materials? And how will we actually use this material? I first heard of ryegrass daggers at Lincoln University in a passing comment by one of our lecturers, and I thought it rather odd that no one actually could explain it. Nothing more was said. And in the 1970s, we had no knowledge of endophyte, With ryegrass pastures then, it was a hit and miss whether it had endophyte present or not. We had to wait a few years to learn more about this. Today, of course, it is a major area of science, and we have the international conference here this week. The discovery in the early 1980s that the common ryegrass endophyte in pastures could cause both ryegrass staggers and insect resistance was a major breakthrough in our understanding of pastures in New Zealand. Soon after that, I ended up doing my PhD on endophyte, which was one of the first in the world on this topic. It absolutely fascinated me, though, that although ryegrass came from the European region, they didn't appear to have many major insect problems. Yes, some, but nothing really like New Zealand. Why is that? New Zealand is quite different from continental regions. We are typical of islands with a very limited range of flora and fauna and few natural predators in our insect fauna. New Zealand's isolation has led to a distinct and quite vulnerable ecosystem, while the continents had much more diversity and established insect communities with more natural biocontrols. Today we have consistent delivery of selected endophytes in seed, offering tailored insect resistance with reduced livestock toxicity. A really remarkable transformation in pasture science over the last 40 to 50 years. However, finding ryegrass endophytes which can control grass grub still remains elusive. To date, the molecular technologies have generated an enormous amount of information about genes, genetic pathways, germplasm relationships, enabled the development of genomic selection and allowed large advances in animal and crop breeding. But surprisingly few pasture cultivars anywhere in the world. Looking at major crops, we see a predominance of simpler, single-gene GMO traits such as the herbicide resistance. Most of the traits we are dealing with in pastures are controlled by multiple genes and are not simple. In addition, our grasses and legumes are cross-pollinated populations, and the complexity of breeding and dealing with those has been seriously underestimated by everyone involved. On the other hand, molecular technology has been very helpful in our endophyte world of simpler clonal genotypes. There is considerable potential for success, but it will require close cooperation of molecular breeders, field breeders, and probably 20 years or more of strong funding and collaboration to achieve it. Easing of New Zealand's regulatory environment should help, but in reality, the issue may be the large cost of such programs in a world of relatively low-value forage, particularly compared to the major international crops. Our pasture industries get a lot of criticism from the environmental perspective, both from nitrate, leaching and greenhouse gases. However, I want to remind everyone of the unique nature of our clover-based pasture systems. New Zealand leads the world in these. Many countries aspire to use legume-based systems, but only a few countries effectively achieve it. Almost all other grass-based systems rely upon nitrogen fertiliser. To manufacture 1 kilogram of nitrogen fertiliser requires 1.5 kilograms of natural gas or oil, with all their corresponding CO2 emissions. We're in the game of converting sunlight to food, not oil to food. We should be very proud of our clover-based grazing systems. Very few farming systems overseas effectively use clovers. Nevertheless, we do get nitrate leaching and greenhouse gas emissions from our high fertility farm systems, and we are challenged with reducing them. We're learning a lot about nitrogen leaching from a large number of trials and unique effects of plantains and other species. In the future, we hope to breed ryegrasses and other species with less nitrate or nitrous oxide emissions. Approximately 50% of New Zealand's greenhouse gas emissions comes from ruminants, and this looks bad. While in industrial countries, their ruminant emissions are equally bad, but the ruminant emissions pale into insignificance beside their industrial output consumption of oil. So although ours look bad, everyone else is worse. Breeding plants that can reduce emissions on farm will become essential. A number of plants offer potential reductions in methane, including AgResearch's high condensed tannin white clover and their high lipid perennial ryegrass. But one of the overarching questions, though, is can farmers actually get a premium price for reduced greenhouse gas emissions? How do we achieve that? Already, many of our temperate grass and clovers are becoming less suited to northern New Zealand as kikuyu and other low-quality subtropical grasses spread further south. In this slide, you can see an expected expansion of the subtropical grass paspalum up to about 2,100 for one of the worst predicted climate scenarios. We expect kikuyu will be pretty similar to this. Grasses, though, are not alone in their expansion, as a number of serious insect pests are moving south too, particularly African black beetle, but numerous others. And in fact, the pest expansion may be even more serious than the subtropical grass expansion. There are a range of subtropical grasses that we can look at, and looking at farming systems where these occur overseas provides some perspective. Many are productive plants in summer, but all will need additional winter pastures to provide a year-round supply. This probably means sowing annual or short-lived ryegrass or some forage crop to the desired amount, get the desired amount of fodder to have fodder throughout the year. Unfortunately, this means higher costs for farms, higher costs than a productive perennial ryegrass clover system. Also, with many tropical grasses, it's not easy to develop a mixed legume system. International breeding companies are actually in quite a good position to breed for climate change, as they already have breeding programs overseas in warmer climates and can introduce these locally. I'm very confident in the future that yield gains will continue to occur in plant breeding in many of our species, and that endophytes will be further improved. The use of molecular tools such as genomic selection should become applied in more major species, but probably unlikely in the minor ones. The challenge will be to develop innovative and valuable traits via mutations, gene edits or GMO, and this still will remain difficult for multi-genetic traits. For sure, we'll see a few major projects with gene editing and GMO, but the politics, regulatory requirements, complexity and funding will limit these to only a few very significant projects. We have the challenge of breeding to reduce environmental impacts, and we're only now learning about the genetic variation and potential for selection. Climate change effects are occurring relatively slowly, and the plant breeding process should actually be able to keep up. Nevertheless, many impacts of climate change will be very disruptive. We've also not yet seen the impact of artificial intelligence on our plant breeding and our agricultural industries in general, and the impact of that's actually quite hard to imagine. Many agricultural chemicals will become restricted and pest control options will become even more limited than today, a situation where endophyte technology is likely to become even more important. New Zealand's land use patterns will likely to change in ways we can't foresee, and much of the arable land in New Zealand may be in demand for dairying, international seed crops and other uses. Production of grass and clover seed may struggle to be price competitive, and seed may have to be grown elsewhere in New Zealand or even overseas. We are likely to see enormous changes in markets and farm systems in ways we never expected. I'm actually now approaching retirement after 47 years of a wonderfully interesting plant breeding career. What could have been better for someone growing up on a farm than to get into a creative side of agriculture and plant breeding? It has allowed me to develop many significant cultivars in New Zealand and internationally, and it has taken me around the world many times. I can assure you that although I may retire, my childlike curiosity of everything will continue. Thank you for listening. I will look forward to discussing anything of this with any of you. So.
Thank you, Chris.